Hello, everyone. So I just want to take a couple minutes and go over the heating and cooling curves. So I just drew up a blank heating curve on here. I just want to go through all the basics and really everything that you need to know that we can fit onto one slide here. So here's your basic setup. Your X and Y axes. Your X axis is your time, and then your Y axis is your temperature, and the line represents the substance as it's going through a temperature change or a phase change that we'll go through. So all of these slope parts, so you kind of break it down into two sections, right? You have the slope parts and then you have the flat parts. So the slope parts represent our phases of matter. So here's our solid, our liquid, and our gas. All right. And then the flat portions represent our phase changes. And now we can go in either direction here. We can go up the heating curve and then we can go down the heating curve when we're cooling. And we'll talk about that as we go through it. All right. So what do these sections represent? So if we're going up the heating curve, we're going this way. Here is where we transition between a solid and liquid phase. And we call that fusion, right? Or melting. Fusion is the more scientific term that we'll use, going from the solid to the liquid phase, and liquid to gas, which is our vaporization. All right. So anything going up the heating curve, right? We'll talk about whether energy is coming in or out of that as we go up. And then if we're going the other way, if we're going down the heating curve, change color. Now we have gas to liquid, which is condensation, right? And then we have liquid to solid, which is freezing or solidification, right? So as we move in either direction, going up and down, there's things that are happening to the substance that you want to be aware of. So the couple of main things you want to keep in mind is what's happening to the particles and how fast or slow they're moving. That's our kinetic energy. And we want to think about what's happening to the distance between the particles, which would affect our potential energy. All right. And one thing you want to remember is, change color again here. Temperature measures, remember, temperature measures average kinetic energy, average KE. All right, don't forget that. Temperature measures average kinetic energy. Temperature is your speedometer. That's telling you how fast or slow the particles are going, right? Higher up on the thermometer, you're moving faster. Lower down, you're moving slower, all right? So we want to break this down into two sections here. We kind of got our single phases, which would be here, here, and here. Right? And we want to go through what's going on there. So these are all within a single phase. This is all one phase. Right? When you're in these parts, you're in one phase. Right? You're not going through a phase change. So what's happening here is, if we're moving up the heating curve, right? We're going this way. We're going up the heating curve as we move up, or as we go down, our temperature is either going up or down. So when we're in a single phase, our temperature changes. Right? And if our temperature changes, remember what temperature measures? Average kinetic energy. So if our temperature is changing, that means our KE changes. All right? And if my kinetic energy is changing, my potential energy is staying constant. It is not changing, right? Why isn't it changing? Because potential energy only changes during a phase change. And we're not changing phase when we're in these slope portions of the diagram. That's all a single phase, all right? It's one phase. We're going through our temperature is changing, therefore our kinetic energy is changing, which is our particle speed. They're speeding up. And then over here, all right, if I'm here or here on these flat parts, right, this is where we're going through a phase change. Right here, we're going through a phase change. right? Here we're going through a phase change. We're transitioning from one phase to the next. So when we're changing phase, notice what our slope is of the line. 0. Our slope is 0. So our temperature is staying, ooh, that's sloppy. Let me erase that. Our temperature is staying constant, which means our KE, our particle speed, is constant. All right. So now, why is our temperature not changing, even though energy might be added or released from the system? Because all of that energy is going towards changing the potential energy. Your PE changes. All right. Now, what's your PE doing? Well, it depends which way we're going, and we'll talk about that. But why is our potential energy changing? Because our particle distance changes, right? That's what's happening when we're going through a phase change. The distance between the particles are changing, all right? So if we're going up the heating curve from here, we're going up and across. All right, let me see if I can put my laser on, right? If we're going up. So what's happening is our particles are starting out down here, right? So we start down here. We apply energy to the system. Particles start speeding up, speeding up, speeding up, speeding up, speeding up. And then when they get here, now they have enough energy to move into the liquid phase. So then they start spreading out, spreading out, spreading out. And then once they get to the end and they've all moved into the liquid phase, now they start speeding up, speeding up, speeding up, speeding up. And then when they get here, now they have enough energy to move into the gas phase, spreading out, spreading out, spreading out. And then they can start to speed up again and heat up and move up. All right. So anything in that direction, we say is endothermic. Anything going in this direction is endothermic. Energy is entering the system. Okay. And then anything going in the opposite direction, anything going this way, is exothermic. Energy is exiting the system as we're cooling and going down the heating curve. So that's right here. All right. If we're going backwards now, we start up here and now we're slowing down as we're cooling and we're losing energy. And then we're condensing. The particles are coming closer and closer together as we go from gas to liquid. And then we're slowing down, coming closer together and slowing down. All right. So if you're going up, you're absorbing energy. And then if we're going down, we're releasing energy. All right. And sometimes you can use the area below the line to help you out. Think of that as all the stored energy in the system. Right. A lot of stored energy over here, and then a little bit of stored energy over here. All right. So solid to liquid, we're pulling apart, absorbs energy, increasing potential energy. And then liquid to gas, we're pulling apart again, and we're going into the gas phase, right? And then if we're going backwards, coming down, we're coming closer together, gas to liquid, and then coming even closer together, liquid to solid, right? So remember what's going on. Think about it, which way we're going. If we're going in the heating direction, we're speeding up, spreading out, speeding up, spreading out, speeding up. So either your kinetic energy is changing. How do you know your temperature is changing? Or your potential energy is changing. It's one or the other. It's never both. Either your kinetic energy changes or your potential energy changes. When does your kinetic energy change? When your temperature changes. If it's going up, you're moving faster. Kinetic energy is increasing. If it's going down, you're moving slower. Kinetic energy is decreasing. When is your potential energy changing? During a phase change, right? If you're going in the endothermic direction, solid to liquid, you're spreading apart, potential energy is increasing. And then if you're going in the opposite direction, liquid to solid or gas to liquid, you're coming closer together and your potential energy is decreasing. All right. So you want to know what's going on with your potential energies, your kinetic energies, and know the names for the phase changes and the inflow outflow. When is it endothermic? When is it exothermic? Those are important things that you want to be aware of. All right. And the other thing is, where do these temperature changes occur? All right. When I ask you what is the melting point, the boiling point, the freezing point, those are all points on the thermometer. So where does that happen? So if we look at this substance right here, let's trace this over to our y-axis. So I put some numbers here. 30 degrees, right? So 30 degrees is my melting point, right? That's where this substance goes from solid to liquid, right? That's happening at 30 degrees. Different substances have different melting points or different boiling points. So the boiling point is where we go from liquid to solid. So that's happening. Oh, it's a long dotted line I got to make here. Let's see if I can make it. Almost there. All right, that's happening at 80 degrees. So that would be called my boiling point, right? So that's happening at 80 degrees for this particular substance. So don't just assume everything is 0 for melting and 100 for boiling, like water. Different substances have different melting points and different boiling points, all right? So this particular substance melts at 30 degrees, which means it also freezes at 30 degrees. So that's my freezing point too. That's just happening in the opposite direction. Liquid to solid, freezing, exothermic, releasing energy, solid to liquid, melting, endothermic, absorbing energy. But they're both happening at the same place, right? Same thing with boiling point. We can also call this our condensation point. So vaporization and condensation happen at the same place. So that's going to be the same temperature for that substance. The only difference is one of them is endothermic, absorbing energy, and the other direction we're going exothermic, and we're releasing energy, right? So that's really everything on one slide that I wanted to include on here, and to just sum it all up as clearly and concisely as possible. So remember what's going on one last time. All right, we're starting out down here. So we're at negative 20 degrees right now, a solid, okay? So we start adding energy to this solid. Right? It starts heating up. Particles are speeding up, moving faster. Kinetic energy is going up. And then when I hit 30 degrees, now I have enough energy to start pulling those particles apart from each other and moving them into the liquid phase. All right. So when we're going through a phase change, right, both phases are present at the same time. Right. When we're going through a phase change, we have two phases. The phase you're changing from and the phase you're changing to. So as we're going through this process, we're going from solid to liquid, pulling those particles apart. And then when we get to the end, now all of those particles has pulled into the liquid phase, and then they start to speed up again. Kinetic energy is going up. And then they get here to 80 degrees. Now they have enough energy to go through another phase change. Pull apart, liquid to gas, pull apart, and we get to the end. Now we've all transitioned into the gas phase, and they start to speed up again. All right, this is all absorbing energy, endothermic. It takes energy to speed up the particles or pull them away from each other, right? But now if we flip things around and we cool things down, now we're slowing down. Kinetic energy is decreasing. Then when we get to our plateau here, our flat, now we start to come closer and closer together again, closer together. And then we start to slow down. Kinetic energy is decreasing. Come closer together. Potential energy is decreasing, and then slow down again. All right. So that's our heating and cooling curves in a nutshell, as quick and concise as I could make it. Thank you.